Okay, thank you, Said. Okay, so this is a very perfect time for opening. So, okay, Daniel already joined in this room and he's ready to deliver his lecture. So, welcome in the first lecture of MLSS Indonesia. I am Ade Romadoni, a lecturer at Telkom School of Computing, Telkom University. The first lecture is Basic Machine Learning that will be delivered by Daniel Borrell. Before I introduce Daniel briefly, I will remind you about the rule in this lecture. First part, the lecture will give the talk in maybe approximately 1 hour and 15 minutes, and we will have a discussion, question and answer session where you can ask questions through Rocket Chat, or you can raise your hand when the moderator will give you chance to raise your hand. So we think about whether we should have a break in the middle of the session, or we can do a question and answer at the end of the session. I will inform it later, okay? And you can prepare the question on the Rocket Chat before, so Daniel and I can look for the question. Okay. Next. Okay, so I will give introduction briefly about Daniel. So Daniel is a postdoc in Max Planck Phillips Group with the Amsterdam Machine Learning Lab at the University of Amsterdam. He primarily works in the field of equivariance, extending convolution beyond translation to other kinds of transformation. Daniel grew up in Cambridge, going to school and later reading engineering at Sydney Sussex College, Cambridge University. And after Cambridge, he immediately began a PhD under the supervision of Gabriel G. Brostow, who is professor in computer vision and computer graphics at UCL. Okay. Yeah, Daniel, can you join?
Hi, can you hear me?
Yeah. Okay. So I think that you will give more introduction about yourself.
Right, okay, yes, perfect.
Yeah.
Well, thank you for a very, very nice introduction. I probably should add to this that I have a personal connection to Indonesia. So my mother was born in Bogor in West Java. So this is a very personal thing for me to do. And I'm very honored to be giving, well, one of the first lectures of the summer school. Can I just check that the sound quality is working here? It's, I think it's a new experience for me giving a lecture on Zoom. People can hear me correctly? Good? Okay, perfect. Thank you very much. Okay, so let's just launch into this. I'm gonna share my screen.
Okay, yes, please, you can share your screen.
Okay, let's see if this works. Right. So you can see my opening slide.
Yeah.
Can everyone
Okay,
see
yeah.
that? Perfect.
Yeah,
Okay,
looks
yeah,
perfect.
so we've got a very nice picture here of Bromo National Park. Unfortunately, people can't go to Indonesia, but if I'd gone, I'd have suggested this would be one of the lovely places you could have visited. It's a really magical place to go. Right, so, okay. Today, I've got about an hour and 15 minutes with maybe a 5-minute break in the middle so people can go to toilet or take a drink of water or something. And I'm going to be discussing machine learning basics. So we're going to cover things like what is machine learning, a lot of probability theory in this first lecture, a bit of generative modeling, some Bayesian inference and statistics, and an applied case of polynomial regression. And this is supposed to be basics. It's difficult to design a course like this because there are people from bachelor's level up to PhD level. So you're a very diverse class, and I know some of you will find this easy, but some of you will find this difficult. And my advice is, do not worry if you find this difficult or if this goes too quickly, because this is only 1 hour and 15 minutes, and I see your entire schedule for the week. It's jam-packed. I'm really impressed that you're going to get so much like tuition in this course. So don't worry, you are not going to remember everything. If you remember 20% of this course by the end, you'll have done very, very well, I think. And the good thing though is that you get to keep the slides afterwards. So the intention is not for you to understand everything today, but to have exposure so that you can go back and read up on these things after the lectures. Okay, so let's jump straight into it. My recommended reading list, I think this is always good to have. These are 3 of my favorite books. My very favorite one is by the late David Mackay, Information Theory, Inference, and Learning Algorithms. It's a beautifully written book, honestly, my absolute favorite. Very, very entertainingly written as well. If you'd like to get more of the sort of the fundamentals of machine learning, I'd suggest this book by Chris Bishop on pattern recognition and machine learning. It's in depth and it's a very, very good base. Our master's course in AI at the University of Amsterdam, we use this book as our sort of our backdrop. And I think a very, very good book by Kevin Murphy on the right is Machine Learning, a Probabilistic Perspective, which is a very, very detailed book. Not written to be easy, but it's written to give a lot of breadth and depth at the same time. Right, so you probably all know what machine learning is, that's why you're here, but I found this quote in a book called Mathematics for Machine Learning, which came out, I think, last year, which says, machine learning is the latest in a long line of attempts to distill human knowledge and reasoning into a form that is suitable for constructing machines and engineering automated systems. I think this is a very, very nice attempt. It sort of gets away from the hype that you tend to see in a lot of articles online, and I think it really sort of, it pins it down, attempting to distill human knowledge and reasoning into a form that is suitable for constructing machines. But I don't really think it's good to try and define machine learning per se. I mean, it's built from many different fields. Supervised learning, which I'm going to really focus on in this first 3 lectures, actually. Reinforcement, lots of computer science, unsupervised or representation learning, information theory, self-supervised, and the list goes on. There is a lot of different subdisciplines or other disciplines which intersect with machine learning. And I think you're going to get a good sample or taster for a lot of these disciplines today and in the rest of the week. But there's a lot of stuff going on. And so I certainly don't know, I'd say half of these fields in any depth. It's just a massive area and it's continually expanding. So it's a very exciting time to be in the field at the moment. But we're going to be focusing today, at least, on supervised learning because it's an easy-ish area. It's one of the more well-developed areas. We've been working on it for a long time. And so let's just go into the basic sort of mathematical description or high-level description. So a supervised learning problem has 3 parts. You have inputs, you have outputs, and this forms your data. And we want to learn a function mapping from inputs to outputs. And this is called a model. And we have a space of these models, which I'm going to give this letter curly m. And basically the idea for us is to try and find a mapping or a model which best fits this data. And we say, find a best model M, and this symbol means in the set of all models. And so, for instance, one example would be classification, where we are taking in an image, and then we put it through a function, maybe this should be an M instead of an F, and it spits out the word owl. This is image recognition. Another example would be I feed in a molecular graph structure like this, and I want to know some property, like what is the binding energy or what is the melting temperature of this molecule, and then we could have a function which spits out the answer. It's a mapping from inputs to outputs. We're just learning functions. It's pretty simply put. So a couple of examples. Here we have image classification. So the inputs are going to be these 256 by 256 pixel RGB images, and the outputs are going to be discrete labels: dog, cat, orangutan. And the question is, what model do we use? Well, we're going to find out in the next 2 lectures what you would use for these particular images. And so we're going to collect samples of the images with their labels. And one suggestion would be to use a lookup table. So if you have a new input, what we do is we see if this input already exists in the lookup table, and then we just select the label which corresponded to that image. But this obviously has problems. What if we've never seen this particular image before? There's a lot of different images that you could have. What if we feed in something which is not a dog, a cat, or an orangutan? What do we do then? What if I have a giraffe or a chair or something like that? How do we deal with that? And how do we even know whether the model is good? Because our models always make mistakes. That is a fact of machine learning. So how do we deal with this? Another example, this is the opening line from one of my favorite books, Bumi Manusia, This Earth of Mankind in English, by a fantastic Indonesian author, Pramudina Tatur. I'm not going to read out the Indonesian because my Indonesian accent is terrible. Although I learned it when I was a child, my mother always says that I don't speak very well, so I won't try. But I've got a task here of translating this Indonesian passage into English. And so the original translator of the book into English, an Australian chap called Max Lane, he provided one possible translation. I tried my own hand at it. Google Translate has another one. And if you actually look at these different translations, there is no one correct translation. They're all different, but they all say the same stuff pretty much. Maybe the Google Translate one is a bit bad, I'd say. And I think maybe Max Lane's, because he's a professional, is better than mine, but it's very difficult to know which one's best and which one's worst, and how to even quantify that. And basically we have a one-to-many mapping. There are many different possibilities for this task. It's not like dog, cat, orangutan. There are many different outputs now, which could all be correct. So this is a difficult task because we have variable length input strings and output strings. Each word has multiple translations. And yeah, just like in the image example, we can't possibly connect everything. And how do we even know what a good translation is? So many of these problems actually can be addressed with probabilistic thinking. And this is what we're going to be talking about today. And I think Shakir Mohammed will also talk about this to some extent. And these are examples of the input-output problems, the classic one being regression. So here we have real valued inputs on the x-axis, and we're trying to predict some sort of function, say in blue, given samples, where the output is the height on the y-axis. Again, how do we handle errors, residual errors in this, because we can't fit all of these points perfectly? Is a linear model the best we can do? Well, clearly not. These are non-linear. And what about higher dimensions? How do we deal with multiple dimensions? Most of this talk today is going to be in one dimension, but we're going to make a jump to multiple dimensions, I think, in the next lecture at, well, in 2 hours, 2.5 hours, I think. And all of these examples are really just the same thing. They're just input-output mappings. So that's what we're going to focus on today. So machine learning, so primarily conceptual discipline, and some could say it's automated machine building. No longer are we actually writing programs and we're hard coding all of our rules in. There's a component of learning from data. So there's many different things of what machine learning is, but you need computers, you need programming, but you also need mathematics. And so this is going to be a very mathematics heavy few days for you guys. Sorry if you don't like maths, it's just the way it is at the moment. But I should also caution this with the fact that there are other aspects which are now sort of being born in the field, like fairness, ethics, decoloniality. You're going to hear about these, I think, later in the week, which take a more societal angle on the field. I'm very excited about these, although I am no expert by any measure. So it's not all about maths, but I think mathematics is the language which we work in, and so you need to be able to speak the language before you can start, writing poetry. It would be my analogy. Right, okay, so let's just jump right into it. Probability and statistics. This picture is from Gunung Kawa Ijen, which is a huge crater in eastern Java, near Banyuwangi. And at the bottom, they have these sulfur emissions, and they light up at night, and it's called the Blue Flame. And a super magical place if you ever get to go there. Right, so my first example, I should have actually picked a volcano in Indonesia, but that's not where I had my data from. There's a publicly available data set from the Mauna Loa volcano on the island of Hawaii. It's one of the largest volcanoes in the world, I think, in both mass and volume, dwarfed only by the Tamu Massif. And what scientists have been doing for a long time is they've been placing carbon dioxide sensors on different parts of the volcano. And over the years, they've been monitoring the carbon dioxide part per million concentration in years. So you see years along the bottom from the 1960s up until the present day. We're over here now. This was some time ago. And you see, this is not actually a curve. If you've got good enough resolution, you can see that there are lots of points. These are actually lots of individual points. And what we do in machine learning is we take data like this and we ask ourselves to make predictions about the future. So what happens if I have this data here? What happens to the right of this data? And actually, because we can't really, no one can actually make predictions about the future. It just doesn't work like that. We really want to know about how much we trust our predictions. So if you can also see, because of the resolution, I have some error bars here on this slide. So we want to make predictions and we want to know how confident are we about making our predictions. And this is a lot of what machine learning is about. You can actually turn these input-output tasks into prediction tasks. Prediction is not always about the future. It's about what we say is called generalizing to new unseen data. We'll talk about that more in the second lecture. But there are some basic questions before we get there, like how do we model these graphs? Do we use a linear function? Well, clearly they're not linear. There's a periodic component. So we might add a little cosine over here with a tunable amplitude and phase offset. But also this doesn't work very well because for certain values of x, this y is going to be negative and you can't have negative carbon dioxide concentration. So I thought about how we model this, and to be honest, I can't come up with a good model. And there's a really good quote by a guy called George Box from a book by him and another chap called Dapper, which says that all models are wrong, but some are useful. And I think this should be the sort of the central philosophy that you always remember as a machine learner. All models are wrong, but some are useful. And okay, if all models are wrong though, is that the end of it? Well, no, because some models are better than others. And so probability theory is a good way for us, and statistics is a good way for us to say, this model is better than that model. This is how often we think it's going to be making mistakes. And it gives us a way to quantitatively define some of these ideas. So we think, or I think, this model here with the periodic component is better than the linear one, for instance. But how are we gonna quantify that? They're both good approximations to reality. So this is done in this field of probability and statistics, and I've just stolen a quote from an old lecturer of mine, Carl Rasmussen, who does a lot of work in reinforcement learning and Gaussian processes. He wrote a book on Gaussian processes, which is very, very good. Rasmussen and Williams, I think, are the authors. Probability is a mathematical formalism describing certain events. The science of collecting and analyzing data is statistics. And this probably will not make so much sense now, but we'll get into it and you'll see. And an area of statistics which is much loved by machine learners is Bayesian statistics. And I'm going to hopefully try and answer to some degree why it's useful, what we can say about uncertain events, and what can be measured. Okay, so let's actually do some maths now. So, okay, recap. Hopefully this is a recap for most people. Take a coin, we'll label one side heads. So this is the head side, the other one's tails, and we're going to associate those with a number 1 and number 0. Now we flip the coin n times and take the average. And we do this multiple times. Say, if I flip it 10 times and I take the average, I get 0.5. I do it again, I get 0.8, again 0.6. Now I increase the number of times I flip. So I increase the numbers in my averages, I get 0.48, 48, 48, 54, etc. And as I increase the number of flips, these numbers on average all seem to get closer and closer to 0.5. So despite the fact that we get a different result in each trial, there is a trend, which is that all of these numbers seem to be getting closer and closer to 0.5, and the distance between them, what we call the standard deviation, is getting smaller. So what happens when n goes to infinity? Well, I've done this here. I did this for my lectures. You have a number of flips along the bottom here. 1 million is close to infinity for us in practical terms. So infinity is off the right here, and this is our average. If we have one trial and we increase the number of trials that we do, we sort of get this behavior here that all of our averages converge to a number. And so there is something about this number which is descriptive and inherent about the coin flipping process, and that is the probability of getting ahead. That's what this number over here means. So probabilities can represent frequencies or the averages of like these coin flips over a very, very long running period. And so if this is the number of heads we have divided by the number of flips, our probability of getting ahead would be this number here when n goes to infinity. And we call this thing probability of heads, little p of h. Those of you who know a lot about probability will say, no, this should be a big P. In machine learning, we're quite lazy. We always use little p's for everything, pretty much. But I recognize there is different notation. So this thing called the event probability is the long run frequency in a repeatable experiment. Those of you who know about probability will know that there's other ways to define probability. So there's a very big one is this thing called Bayesian probability, and it represents beliefs. So given the results of a blood test, the probability that Sridewi has a nasty disease is p%. Sridewi hasn't gone to the doctor 100 times and taken the average of 100 blood tests. This is a percentage that we can give to a blood test which was taken once. The probability that Gunung Merapi, which is a volcano in Java, will erupt on the 31st of December 2020 is q%. We can't even collect this data because it's not even the 31st of December. So this percentage gives us a belief about the future which we haven't yet encountered. We cannot run this experiment multiple times because the 31st of December will only ever happen once. So, as I say, such claims cannot be verified through repeated experimentation. This subjective interpretation, or what's called the Bayesian interpretation, expresses a degree of belief. It's not something we can test necessarily so easily, although there is a connection between this previous frequentist view of probability and the Bayesian view. I put this picture of the Reverend Thomas Bayes, who is sort of accredited with coming up with Bayesian statistics. I've learned a lot since then. Apparently this picture isn't even of the Reverend Thomas Bayes. Someone pointed out to me on a side note, but go figure. This is the picture everybody always uses. But the really nice thing about these two areas of, or two intuitions or two schools of mind on probability is that they are both treated with the same theory. So it doesn't really matter what you think about probability and what I think about probability. We're using the same mathematical theory, which is super nice. And actually, I think some of the lectures later on are going to actually show you that there are many other interpretations. So you can interpret a probability as a propensity, a logical statement. There's a very good book by a guy called E.T. Jaynes, Jaynes, which goes into this. It's mechanistic. This is probably more close to the machine learning interpretation. So there's lots of different ways to view probability, but it doesn't matter because the maths is the same, which makes our lives a lot easier. Okay, so what are the foundations of probability? These are called the Kolmogorov axioms or probability axioms. This is the guy Kolmogorov who sort of put these together. So essentially, if we have an event X, so this event might be the event that I get heads when I flip my coin. This is always a non-negative real number. So it's 0 or bigger. Certain events, so things which are always going to happen, have a unit probability. So now we know that the probability is bounded between 0 and 1 inclusive. And countable additivity. So the probability of disjoint events, so events which do not overlap, they sum up as the sum of the individual events themselves. And it's amazing that you just have these 3 rules, and from these 3 rules you can prove everything in probability. Everything you're going to see today, everything you'll read ever in a book comes from 3 rules, which I think is really quite marvelous. And there's a lot of other things. This is really just a recap. You don't have to read through all of this now, but we have complement rules, impossible events are 0, probability of more likely events are bigger than probability of less likely events. And in general, the probability of 2 events happening together is the sum of each event minus their intersection. But don't worry if you haven't seen this. I think it will take a lot more time to understand this in just 2 minutes. But this is just, as I said, to give you intuitions and to give you exposure. Okay, just a bit more. Probabilities are defined on top of sample spaces. A sample space with this denoted by this big omega is the set of all possible outcomes of an experiment. So in our coin flip example, our sample space would be to get either a head or a tail. These are the 2 possible outcomes of that experiment. An event is a subset. So a subset is basically, well, it's a collection of samples. So the subset for us, the possible events that we could have for the coin toss experiment are nothing happens at all. We get a heads, we get a tails, or we get a head and a tail. These are 4 different possible events. And the space of 4 events is called the event space. It's also called a sigma algebra. And it's a subset again of the space of all possible events. These things can get very complicated when you deal with continuous spaces. So we're not going to go into that. We're just going to give you a working idea. And so probability mass functions are defined on event spaces. They map each event to a number between 0 and 1, 1 being that event definitely will happen, 0, that event will never happen, and something in between that the event may happen with a certain probability. Actually, I just described this, and yeah, the basic idea is bigger probabilities correspond to things which are more likely to happen. And to give you a working example or working feel for probability, there are 2 rules which are, oh no, actually, no, we're going to come on to that in a bit. There are 2 more things we need to introduce. One is joint probability. So I can give you the probability of an event A, I can give you the probability of an event B. The joint is the probability of both A and B occurring at the same time, so A comma B. So this might be the probability that it's raining in Amsterdam and that I forgot my wallet when I went to the train station. Random ones I just chose now, but there is an intersection. Maybe on rainy days I'm more forgetful because I had to remember to put my jacket on and I left my wallet on the floor or something like that because I was wearing my jacket. Silly example, but it's the probability of things happening together. Conditional probabilities, on the other hand, and by the way, these events, as I said, they're subsets, so we denote them by these shapes here. Their intersection is when they both intersect like this. Conditional probability is a different idea, which we write P, A given B like this. Oh, sorry, I've got big P's in the diagram and small ones outside. Sorry about that. They are the same letter. conditional probability is this idea of when an event happens, given that another event has already happened. So in our example of me forgetting my wallet and it being rainy, maybe B is the event that it rains outside, and A is the event that I forget my wallet because B had already happened, because it was raining. And there's a convenient rule here. So essentially this probability, this conditional probability, is the shaded region here as a proportion of all of the probability of B. And we represent this actually as a fraction. It's the ratio of this area here, which is the joint actually from over here, and the probability of B. So it's sort of renormalized in a sense. And note that is not symmetric, unlike the joint probability. Right, and these two rules, which I'm going to show next, are pretty much the only rules you ever have to remember when you're dealing with probabilities. One is the product rule. It tells you how to decompose a joint into the product of what's called a marginal, P of B, and a conditional, P of A given B. And actually you can just see this from the definition of conditional up here, just rearranging it. And the sum rule, which is how to get a marginal from a joint. You just integrate out or sum out, depending on whether you're dealing with continuous or discrete events, all of the terms in the joint which don't appear in your marginal on the left-hand side. So here we're integrating or summing out B. And from these two rules, pretty much, these will make your life a lot easier. Most machine learning papers, you just have to remember these to read through all of the probabilities. Makes life a lot easier. And there's some proofs on the bottom here. How are we doing for time? Okay. And just to, this is just another slide, just chock-a-block with mathematics. Again, I would go actually follow a course like in a book on this, or maybe go to Coursera or see some online video courses if you really want to get more in depth into this. A very famous rule which you're going to need to know, especially for today, is Bayes' rule, which is just a way to convert conditional probabilities of y given x into conditional probabilities of x given y. And this is very easy to show from the fact that we can decompose our joint distribution into this using the product rule from before, or this other way around. Because this is symmetric, we can say x and y, or y and x are the same thing. We can decompose, and then if we divide both sides by p of x, we end up, or p of y actually, we end up with this rule up top. Change of variables formula, I won't go too deeply into, it's just on the slide for your, just so you have this when I send you the slides. It's just a way to convert from probability densities in X to a reparameterization. This is very big in the area of normalizing flows, if you ever come across that. Expectations, these are things like computing the mean, say, of a probability distribution. That's a form of expectation, and it's given this funny, I don't know what you call this, like a kind of a calligraphic or stencil E symbol. And we write the probability distribution, which we're taking the expectation with respect to on the bottom. And then we put whatever function we're actually forming our expectation over inside. So a mean is written like this, and a covariance, which is a form of variance for multidimensional quantities, would be written as such. And then there's a couple of extra things down here. Again, if you haven't seen these, go and read about them. I think the good thing about this lecture course, or this entire course this week, is about exposure, but really you should be empowering yourselves to go and read about this stuff. It's the best way to learn, I think. So a couple of these extra ideas. There's a different view on probability, which is sort of called information theory, and it's quite interesting. Actually, I'm going to skip this part because this isn't so relevant for today's stuff. But again, I would read the book by David Mackay if you want to understand what these quantities mean. And I think Ian Fisher's going to give you a very in-depth view of all of this stuff anyway. Right, so now we're going to get on to probabilistic modeling. That was a, 10-minute crash course on probability. You're all experts now. Let's go into what we're actually interested in. So this idea that we were looking into before was we want to do supervised learning. We want to say, given this image, what is it? Well, you can actually propose that in a mathematical way as a conditional probability, what's known as a discriminative model. Given an image, what is the probability that it is a cat, a dog, or an orangutan? That's a conditional probabilistic statement. And so we're going to have to phrase all of our models in this form, P of X given theta. Here, normally we would say P of Y given X for a predictor. Here we're doing something a bit more simple for the moment. We're just going to be looking at some data, X given some parameters, theta. But these ideas, they translate across many different problems. Right, so in this particular case, for us, we are not looking quite into supervised learning yet. We're looking into just unsupervised models. We're just trying to model a density in X or a distribution in X. And so X would refer to observations, and we are given a set of parameters, theta, and this basically models our emissions. So we start off with these probabilities or these parameters, theta, and we're going to sample from this distribution multiple times. We're going to be drawing data. We're going to be observing the world, and we will get a data set x1, x2, etc., all the way up to an xn. And the distribution of these samples will closely match this distribution here. So an example is you're a physicist and you're building a model of radioactive decay. And our model says particles decay X centimeters away from a source following an exponential distribution. Actually, let's have a look at what this looks like. This is our source. This is some sort of distance away from the source, and these asterisks here represent the point at which a particle decays. So maybe a particle is moving along here and then it splits into other particles, and we can measure the point where it splits at these points. And these distances are distributed according to what's called an exponential distribution. And this has this form, P of X given lambda, that was theta before, and this is written in this form. We have an e to the minus lambda x divided by some number called z. And this number z here is a normalization constant. It's designed so that the integral of this top part always equals 1. So if you take the integral between 0 and infinity, we're going from 0 because x has a minimum value of 0, infinity, maximum value. Integrate this, it should equal 1. If you do the maths, z is equal to 1 on lambda. So it should be lambda e to the minus lambda x. This would be one example of a probabilistic model of x given lambda or theta. And different values of lambda will give us different distributions, and we can see those over here. This is distance along the bottom, x, P of X given lambda over here. So bigger lambdas make this distribution come closer into the y-axis. Right, another example, a more complicated example of such a distribution to model these emissions would be a gamma distribution. This is very related to the exponential. Again, we have this e to the something component here, but we now have an extra monomial coefficient at the front here. So if alpha is equal to 1, I think you can see that in here, this blue and this orange curve. This just reduces to an exponential. And now we have two parameters, and we also have a normalization coefficient. Some clever people figured it out that it's this, which is a ratio of a gamma function and a beta to the alpha. Okay, so we have a distribution for how individual particles will decay at a distance x from the source, but how do we model multiple observations? How do I talk about the probability distribution of all of these samples together? Well, we talk about a joint probability. This is a joint event. This is the probability that we have particle 1 decaying at x1, particle 2 decaying at x2, etc. together. So this is great. We already know how to work with this. We have a joint probability. And we can expand this out using the product rule as we showed before. But what you will find is that it's a very complicated statement. And so there's this idea which we come across a lot in statistics and machine learning called independence, or in this case, marginal independence. And this basically says that the probability of each observation is independent. It doesn't depend on other observations. And it's identical. So we're saying that each particle comes from the same distribution, and where it decays does not depend on any of the other ones. This is what's called an inductive bias, an assumption about how the world works. And this basically says that the P of this conditional distribution, P of x1, given all of the other x's, well, it's just the probability of x1. So when we write this out, we can actually just write it out as this product of marginal distributions. That's really, really nice. There's actually another definition which will be useful for us because our joint is actually like this. It's written as P of x1 to xn given some theta or given some lambda. And conditional independence is basically saying that these two things, x1 and x2, are independent, but only when we have seen something else, only given an extra piece of information. So for us, this extra piece of information is the parameters theta. And in our way of thinking, which is a very Bayesian way of thinking, theta itself is also a random variable, actually. But yeah, so these are the two different ways of describing independence. In a lot of Bayesian mathematics, there tends to be actually a more complicated version called exchangeability. Again, you will come across that if you come across it in a paper. It's quite complicated to explain at this stage. Yeah, so how do we apply this to multiple observations? Well, okay, hopefully you agree with me that the probability of these multiple observations given the parameters lambda is a joint, conditional on some lambda like this. Now we're going to use our conditional independence criterion to rewrite that as a product of these conditionals like this, because we just talked about that. And then we're going to substitute in the law that we have from before into this. So we get this form here, and if you work that all out, you get this complicated expression over here on the right. So this is really nice. This now gives us a probability distribution in multiple observations x given lambda. We can do the same for the gamma model, and then we get, okay, something like this. Now we have two parameters here on the right. We can write that out again as these conditional statements. So this is xn given alpha and beta, and you substitute in the gamma model and you get some mathematics over here. And you can probably, I think you can simplify this even further. That's more sort of left as an exercise for you guys. Right, so that's a way of describing a model. And what we've just talked about is something called a forward model. To some extent, it's part of what's called a generative model, but it's only one part. And this is our assumption of how the world works. So this is my assumption of how, say, particles decay. Given a theta, what is the distribution in x? That's very, very interesting if you're a scientist, but not everyone here wants to be a scientist. Sometimes we're actually interested in the reverse process. We're interested in reverse engineering. So we know how the world works in forward mode, but what about in reverse mode? So given our data, x1, x2, etc., what were the underlying parameters of the distribution which generated this data? So this is sort of reverse engineering the world. We're going in the opposite direction. And this is the area of statistics. And I think actually, I gave you definitions of probability and statistics before, but I think this slide here really, at least for me, this encapsulates the difference. Probability is really sort of modeling the world in forward mode. Statistics is modeling it in reverse mode. Now, people are going to argue with me about this, I know, but this is a very simplified version. But I think if you get this, it gives you a rough separation between these two ideas or two areas. Cool. So how do we do this? Well, there are multiple ways, and this is a huge area of research for statisticians. I think the way which is most prominent in the field nowadays is a technique called maximum likelihood. Maximum likelihood is a bit pathological in many ways, but it seems to work very well in combination with deep neural networks. So I think it's good that you get a good understanding of how this works. So again, we have a data set x1 through xn, and we have a forward model, which we know we have a model of how data is generated given parameters. And we want to do the opposite. We want to find the parameters given data. So the idea is, why don't we enumerate? Why don't we imagine or synthetically generate every possible forward model, so for every set of different parameters, and see if it matches the data. So this is my data of emissions here. Maybe this data was generated from this model here with lambda equals 1 for our exponential distribution. Maybe it came from this with lambda equals 2. Or maybe it came from this with lambda equals 5. And in each of these models, I've shown you typical examples of what the observations would look like. So if you look at these three and you eyeball it, you would say, well, probably lambda equals 2. This looks most close to the data which I've shown here on the left. So bearing that in mind, we would say, yeah, this is probably the best one. How do we formulate that in a mathematical sense? Well, what we do is we are taking this probability of the data given the parameters, and we were actually maximizing this probability of this data given the parameters over the parameters. So what this thing says, argmax, I think it stands for argument maximum, because lambda is called an argument. What this does is it returns the lambdas which maximize this quantity. But actually, this isn't a forward probability. So before we had a P of X or P of D given lambda, but now, and this takes a bit of a step change in your head, we're doing something in the opposite direction. We're taking this quantity and we're putting the data in here, and it's now a function of the parameter lambda. So before we had a lambda and it was a function of X on the left, but now we're putting our X's in and it's a function of lambda. And so when you change the way how we use this object, it's no longer a conditional model, it's actually called a likelihood because it's a function of lambda, not of X. So we say that this is the likelihood of lambda given the data, not the likelihood of the data given lambda. And this is, when I first recognized this, I was already 1 year into a master's in this area. So I recognized this very, very late on. And a lot of people still don't get this difference. It's a very, very important one to stress. This is a function of lambda, not of the data. So it's a likelihood. And it's confusing because this notation has this bar in the middle, and we're used to reading this P of D given lambda, but it's not. It's a likelihood of lambda given data. Okay, I'll go for, I'd say, another 5 minutes, and then we can take a 5-minute break. Okay, so we find the maximum by setting the derivative to 0. And if we do that, we get, we can do this, because this is how you do calculus. And another way that people tend to do this is they take the log of this quantity, and then they will take the argmax. And the reason for that is twofold. We like small likelihoods. We tend to use small likelihoods, and this would lead to numerical underflows. So this log kind of makes it a lot easier to deal with. And also, when you take the derivative of the log of the likelihood, it works out a lot easier. The derivative of the log just becomes a sum of terms rather than this complicated thing over here. So applying this to our problem before, we're going to take the derivative of the log likelihood of our data. Well, this is so. If you substitute in what we had before for the likelihood, you get argmax, sum, log, and then you have this thing here, which was our distribution. And then if you rewrite that, so we're gonna apply the log over here, you can rewrite that as this. So you can check the mathematics yourself later. And I've plotted the likelihood here. This is the log likelihood. The true parameters are given in blue. The true parameters do not match the exact maximum of the likelihood because because our data set doesn't reflect reality perfectly. If I had an infinite amount of data, these two would align. Okay, we take the argmax by setting the derivative of this quantity to 0. So we take the derivative. If you do that, you set it to 0, and you get some expression out. So if you take the mean distance and do 1 divided by that, that will give you the optimal lambda. I think now would be a good time to take a 5-minute break. People can go get a glass of water, or they can go to toilet or something. Yeah, I'll see you in a bit.
Okay, thank you, Daniel. Okay, so all you can have a short break, and I see here on the Zoom chat that some of you have a technical problem, and we already reset some of your password, but for anyone else who discovers same problems, okay, we will try to reset your password. Okay, okay, Daniel, and you can also have a drink. Yeah. Okay. Okay, for question, please write on the Rocket chat, Lecture 1 channel. Okay, also some people ask about that, yeah, about the slide. Okay, we already shared the slide on the website, so you can go to the session, Lecture 1 session, and then you can find the slide there. Okay, Daniel, there are some questions on the Rocket Chat channel. Maybe you can
Right.
see, but I think you will give answer at the end of this
Yeah, that's probably
lecture.
a good idea.
Yeah, okay.
Right, so we'll wait another, what, 2 minutes, and then we can start again.
Okay, great.
How am I doing for time? So this finishes at in 40 minutes, yeah? Or
It's until 3 p.m. 3 p.m. So if we will have like a 20 minutes discussion, and then you should end at 20
okay,
20 minutes.
20 minutes. Okay, cool.
Okay.
I think I'll skip 1 or 2 slides.
Mm-hmm.
Yeah, I'm going a bit slower than I thought, but that's always
Yeah,
me.
because that's quite complicated, I think. Yeah.
Okay, 1 more minute, and then I'll zoom off.
Yeah,
Let's see if I can.
please.
Okay, cool.
Yeah.
So on my watch, that's 5 minutes.
Yeah.
So we were doing maximum likelihood. Hopefully this shouldn't be too difficult. You've got your likelihood, you take the derivative, you set it to 0, and then you can find an expression for the parameters. It turns out there's a family of distributions which you can do this for, and these are called the exponential family. And they all have this particular form. You have some some parameters and some function of the observations, and then you have another function of the observations here, and they're normalized by some quantity depending on the parameters. And these are very, very easy to work with. And it's weird why we picked this particular solution, but it essentially allows for lightning fast computation. And there's a couple of things you can work out, but there's this thing called the method of moments, which you can use to compute the optimal parameters very, very fast using something called a mean value mapping. I'm going to skip over these bits a bit fast. You have the slides there, so you can read them at your own leisure later, and you also have all of the key words which you can Google.
Yeah.
As I said, this is for exposure rather than anything else.
Okay.
And you can apply this to maximum likelihood example, and you will get the you'll get to the same result that we did before, but using a much quicker method. And yeah, some nice people have made lists of all of these things. It's very, very easy to use. Right, okay, so now this is a very important part. We've just done maximum likelihood. So we take the max of this thing here, of this likelihood. Is this the best that we can do? It's almost certainly wrong if the parameters are living in a continuous space. The probability that these things, the maximum likelihood thetas are the true ones is actually 0, almost all the time. So that's not very good. And our model is almost certainly wrong as well, as I said, quoting George Block's earlier. So why do we want the maximum likelihood parameters anyway? What would we use these for? Well, maybe we are interested in knowing these thetas. Maybe there's some physical interpretation of them. So on an exponential decay model, this is literally a decay constant. This is a physical constant which scientists are interested in. The other thing you might want to say is actually, we're going to be machine learners. I actually don't care what theta is. What I really care about is about generating new samples, which you're going to call X with a little star on the bottom. And this is this idea of prediction. I collect some data, I might have some underlying model with some thetas, and I understand theta from the data, but actually I'm interested in creating new data X from this distribution. This is what things like normalizing flows or generative adversarial networks do. And actually this is what we're interested in a lot of the time. Can we predict new data from this distribution here? And the main way of going about this is to use something called Bayesian inference. So we can actually think about this as a distribution. We can think of a conditional distribution of a new test point, X star, given our data set. And we can compute it from known quantities. So what I can do is I can take it, I can expand it as such, I can introduce some theta. This is just this marginalization or sum rule written in reverse. This was written on the previous slide. And then I can expand this using the product rule. And then I get a product of two terms. Well, this is just our forward model. And this is another quite interesting quantity which we don't know. And it's called a posterior. And we can actually rewrite the posterior in terms of things that we do know using Bayes' rule from before. And so this is a super important expression here. We can rewrite P of theta given D as P of D given theta, or actually I should say theta given D, actually, likelihood of theta given D, a prior, and some other term P of D, which actually you can derive as, again, a marginal. And so this is called a likelihood, a prior, and a marginal likelihood or evidence term. It's called marginal likelihood because literally we've taken the likelihood and applied the marginalization rule on top. So we wanted to know this P of X star given D. We can actually rewrite it in terms of our forward model and the likelihood and the prior, which is very, very neat. So if you have the likelihood and prior, then you can derive everything. And this is called the probability of the parameters given the data. And it's more descriptive than a point estimate because it gives you a probability for every possible theta that could have generated the data. Rather than just giving you a single theta, it gives you a distribution over every single possible theta. And so one way of interpreting this is looking at the predictions for every single possible setting of theta and then applying an average. This is an average over every possible model you can think of, weighted by this posterior probability. And this approach is called generative modeling. So this is the third way of thinking about probabilistic models in this generative modeling approach. So there's a classic example of a bent coin. You're given a coin which is bent like this. You flip it n times and it lands heads h times. I want to know the probability that the coin lands heads is pi. What is this probability? So let's compute the posterior. Well, we can expand it using Bayes' rule. We can plug in our likelihood, our prior, and our evidence. We need to pick a prior. Well, the probability is going to be between 0 and 1, so we pick a uniform distribution. So this is a uniform distribution over here. And this is a Bernoulli distribution. This is a distribution for ones and zeros. We just do a bit of maths and we get to some result here. And if I plot this, so now I've flipped a coin a number of times. I think here it's flipped 1 time, 2 times, 5 times, 10, 25, 50. And the number of heads I have is shown here. And we see that we have a distribution, this posterior distribution, which gets tighter and tighter around the true pi, which is this number at 0.5. And then we compare that with the maximum likelihood. It just turns out that in this example, the maximum likelihood coincides with the maximum of the posterior as well, because we've chosen a very special kind of prior. But we see that we have the maximum likelihood estimate says it must be this number here, but the posterior is much more forgiving and it says, well, it's most likely that number, but it could also be something close by, but it's very unlikely to be 0 or very unlikely to be 0.25. So the posterior is much more forgiving. And now we can use this. So next we also have to figure out the marginal likelihood, sorry. We had this rule before for a posterior, but we still had this Z term to figure out. Well, you can do a load of maths, and this turns out to be this thing called a beta integral. They're quite scary. Don't worry, they scare me as well. But again, there's lots of references which will show you how to do this. I'm just going to zoom through all of this because it's very, you can read about this. You don't need me to tell you this. But in general, the form of the posterior looks like this thing called a beta distribution. And I've plotted some different beta distributions down the right-hand side. I've got 2 parameters, alpha and beta. It's got some properties. And what we were interested in again is figuring out a new probability distribution. So now that I've seen my coin flipped n times, what is the probability we expect it to be a heads? And you can figure all of this out. Again, it's just more mathematics and you get a rule. And it's a famous rule called Laplace's rule of succession in this specific example. Okay. Again, so we took the maximum of the likelihood function before. Some people also take the maximum of the posterior estimate or the log of the posterior. Sometimes people also do. And you actually see that if you expand this out using Bayes' rule, so we've taken the posterior and we've sort of put Bayes' rule into it here, we can rewrite it as this. And if we take the argmax over the thetas here, well, the evidence doesn't actually depend on the theta, so we can drop it. And so we actually get the argmaximum of a sum of 2 terms, which was the log likelihood and the log prior. So we see that taking the maximum a posteriori estimate is actually just the log likelihood in disguise with an extra weighting on using the prior. And as we have, as our data goes to infinity, if we rewrite our likelihood in the term that in the way that we saw it before, we actually see that this term here dominates. It gets super, super big. And so the map estimate tends to maximum likelihood. People don't actually like to do maximum a posteriori in practice though. because it's got some nefarious properties. Basically, it depends on the parameterization of your likelihood. So people try and avoid this. But anyway, there's these three ways of thinking: maximum likelihood, taking the posterior, or taking the maximum of these things. And actually, in the infinite data limit, all of these things are pretty much the same thing. Right. And there's this idea of conjugacy when you work with these Bayesian models, which is very nice, which is that when the posterior and prior have the same form, and this makes our lives a lot easier. So if you have a likelihood, say, of this form, so this is an exponential family likelihood, and I showed this to you before, and if we have a prior of this form, again, these things all look very complicated. You can read them again in your own time. And I think everybody has the slides now. You can work through the maths, and then you get a posterior of this form here. And the nice thing about these conjugate exponential family models is that we can update the parameters tau and, oh, I have my animations in the wrong order. We can update the tau and the nu using very, very simple rules, which only takes n computations, or order n computations. It's linear in the amount of training data we have. So that is super, super nice, because it gives us the ability to do lightning fast and exact computation, which is super useful. So people really liked these models about 15 years ago. But nowadays people still use this stuff, but if we want to use something more powerful, like a deep neural network for the likelihood function, people have moved on to other things, which unfortunately don't have this lovely property. So how do I compare models? So actually, it's not so difficult. So we can go through this quite quickly. All you have to do is you define a likelihood for your model given your data, and you put a prior on the model, and then you can compute a posterior. And it's really just as simple as that. Then you can compare posterior probabilities. Most of the time, however, the model prior is flat, so all these P of mi's are the same. So we don't even have to do this, because the posterior and the likelihood function look pretty much the same up to a constant. And so taking the argmax of the posterior would just be the same as the argmax of the likelihood. But you can expand this term out as such. And it turns out that this term here is just the evidence. It's just the bottom half of Bayes' rule. So this was our likelihood of our theta given d from beforehand for a particular model. This was our prior, this was our posterior, but this P of d given m on the bottom is our evidence. And this also just happens to be this P of d given m. So if you can compute this bottom term in your Bayes rule, that usually tells you how good your model is. So normally you just pick the model which has the best evidence. So let's see this in practice. Well, I've got some data. I know it's zero mean and unit variance, but is it better modeled by a Laplace distribution, which has this sort of form here, is very peaky, or is it modeled by a Gaussian distribution like this? You can compute, say, a ratio of the evidence for one model and the evidence for another model. So this is Laplacian on the left and the Gaussian on the right. And when you feed in data, so increasing number of points, this ratio will either get very, very large or very, very small. We're taking the log of it, so it will either be negative when it's very, very small or positive when it's very, very large. So data for the Gaussian will make this very small, which says that P of D, the likelihood of M2, so the Gaussian model given the data, is very big. So negative means we prefer the Gaussian. If we generate data from the Laplacian, it goes positive, means yes, actually the Laplacian is a better model. And if we generate data from something else, it says, well, actually this is probably slightly closer to Laplacian, but we're not that sure. So there's a very easy framework for computing the for comparing models. And this is known as the log Bayes factor. And another thing you can do, instead of having individual models, we might have a continuous family of models indexed by a hyperparameter tau. And what we can then do is we can just do continuous optimization on this. And this is called type 2 maximum likelihood, or empirical Bayes, or the evidence approximation. And then, but again, it's just maximum likelihood again. Okay, right, so I've got 5 minutes, and I'm going to quickly, maybe I'll push it out for 7 minutes, let's say. I do a bargain, and we're going to look at a case study with regression. Right, so, okay, so now we actually get on to looking at input-output mappings. So in high school, you learned that the equation of a straight line looks like this. So I can have some f of x, which is has some slope w and some intercept b. This is all very nice. And we can rewrite this in vector notation like this. If we put all of our parameters into a vector and our x's into a vector and take their inner product. And so in general, a function is linear. This is a linear equation in w. And if it's linear, it satisfies this expression here. The thing is, though, we also have noise. This data doesn't fit a straight line. So we say that our observations y are the original function f, which is the straight line, plus some deviations epsilon. And these epsilons are generated from what's called a normal distribution. So a normal distribution has this complicated form along the bottom. And this is what the distribution would look like in 2 dimensions. This can be in any number of dimensions. So for us, this would be in 1 dimension, in which case this would just be the same as taking a cut along the x-axis. And the normal distribution has 2 parameters, the mean, which is the center, and a covariance, or this is actually precision, which is the inverse covariance, which describes how elongated it is in various directions. Right. And then we can feed this into our likelihood framework as before. And then, so we're going to compute a likelihood, which is a probability of, well, it's not a probability, sorry, it's a likelihood of some parameters, w, and hyperparameters, tau, which describe these things like, well, I'll explain what they are in a bit, given data. We can write this out using our assumption of conditional independence from before. And then we can just substitute in our definition of the normal distribution. This tau will correspond to these sigmas here. If we substitute that all in, we actually get a different normal distribution in higher dimensions. You can do some mathematics. This is a good exercise to do in your own time to work out the posterior in W. Given all of these terms, you can work it all out. It happens to be a normal distribution as well, because the normal distribution is one of these conjugate distributions. And it's got some parameters there. This is in all of the standard textbooks, right? And what you see is that the distribution in the W's at the end is a kind of mean. It's a kind of mean weighted by the covariance. And this covariance of this normal distribution is a kind of mean of the inverse covariances of your prior and of your data, which are called precisions. Right. But you probably want to see what this looks like. You can also do some stuff with finding your predictive model from before. You can do type 2 maximum likelihood. It doesn't matter. Okay, so now we actually get to our results. What you can see is I now have some plots with increasing numbers of points. So 1, 2, 3, 4, etc. And I've plotted the evidence for these plots here along the top. And you see the red line is the true underlying line. And what I've also plotted is plus and minus 2 standard deviation error bars. So we're plotting a distribution over our outputs given some inputs. So we have inputs along the bottom X, we have outputs along the Y axis. And what we can do is, because we have a posterior distribution in our models, there's not one model which is favored. We actually have multiple different models which could correspond to this data. And I have sampled, I think, 100 of them in each plot. And you see 100 different possible lines which could fit this data. And these lines have a certain mean, which gets tighter and tighter around the true model with more and more data. Right. And then there are two different ways of fitting this. We can use this evidence approximation, which I just talked about. How do we move to nonlinear stuff? Well, we use a process called featurization. And for that, we essentially, it's quite easy. We can rewrite our observations X in a polynomial form. And if we do that, then actually we can just rewrite it in vectorized form as such. So basically we've taken nonlinear versions of X, and then this is actually still a linear model in the W's. And it's super simple because before our likelihood looked like this, and now our likelihood looks like this. And the only thing that's changed is that we've actually transformed the X's using what's called a feature transform. And designing these feature transforms is an area. It used to be an area of huge research until we moved into deep learning, where we learned the feature transforms. And in my last 2 or 3 slides, we'll just see how this would then work for a cubic example. These are examples of different feature transforms you could use. And so here's an example where I have sampled data from a cubic polynomial, which is these red curves here. So it's the same cubic, and I'm increasing the number of points I've sampled, 1, 2, 3, 4, 5, etc. And you see what happens as I get more and more data is that my uncertainty bars, which I got from looking at my posterior predictive distribution, which was this thing we were interested in to start off with, these get tighter and tighter around the true polynomial the more data I get. But there is still uncertainty when you're far away from the data, which is some desirable property, because far away from the data, we have few examples. It might not follow this cubic necessarily. And if you do this process where you also optimize all of the other hyperparameters in this system, then you get this example here where actually these error bars would be a lot bigger. So if I sort of flick between the two, you've got sort of the standard Bayesian example, and this is this optimized Bayesian example by this optimized evidence. And as you see, using the optimized evidence, you get slightly larger error bars, and your evidences are a bit better because we've directly optimized them. I think I've gone over a few minutes, so conveniently we are at the end. I'd just like to apologize for maybe rushing a bit in the second half. My timing was a bit off. But hopefully, I mean, as I said at the start, though, this is really just to give you exposure to this stuff. It's going to be very, very fast. We can't cover, like, normally this course I give in the space of 8 weeks. So getting that into 1.5 hours is quite a challenge. But hopefully people have been exposed, and if they haven't seen this before, they know the terms which they can look up and where they can find that material.
Right. Okay. Okay, Daniel, thank you so much. And I have seen some questions, like 5 or more questions here. So since we only have like 10 until 15 minutes, so maybe I just invite one participant to ask question in this Zoom meeting. So I will pick one, the first that give question on the rocket chat. Muhammad Kamarul Arifin Kamarudin. Okay, please unmute. Muhammad Kamarul Arifin Kamarudin. Okay, I hope that you still join in this room. No. Okay, next one. Okay, so I will read the question from the rocket chat from Muhammad Kamarul Arifin. He asked that any keywords that help distinguish the meaning of model versus algorithm. I find confusing.
Yeah, I think in machine learning, we're not very clear about that a lot of the time. And there used to be a very, very good distinction between these two things. And with deep learning, these things have become very entangled. I think the easiest thing to do is to say, okay, let's have a look. A lot of slides. So I tend to think of a model as this conditional distribution here. P of X given theta, or in terms of the linear regression, it might be y is equal to f of x plus epsilon, or p of y given x and w and tals. It's, if I can find, here we are. My model is this forward thing. It's going from the theta to the data. It's taking my parameters and generating the data. That's my model. The algorithm is, in general, the way how we find these parameters theta. So that the algorithm is maybe like maximum likelihood. That's a particular algorithm. It's a way of finding some thetas given some data. It might be Bayesian inference. So Bayesian inference is a kind of algorithm in a way, because it's finding a posterior distribution in the thetas. But the original model, the forward mapping from the thetas to the x, that is what I would call a model. And the algorithm is just, there are multiple algorithms you can use to find your thetas given some data. But there is just one true model. But there may be many candidate models, and the algorithm is a way of selecting between these different candidates. Which one best describes the data. But again, this is just my interpretation. People say all sorts of different things. It's yeah, these things are always open for debate.
Okay, so since there are already many questions, so I will inform for the participants that Daniel will happily share the question that can be answered in this session. Okay.
Yeah.
Yeah. Okay. So we go to the next question from Kemas Wiharja. Is it the same, machine learning and machine reasoning?
Oh, I don't actually know what machine reasoning means necessarily. So machine learning is an established field. Machine learning is this discipline which you can study a master's in and do a PhD in. We have conferences in machine learning. Maybe machine reasoning exists. I don't know it personally. I think machine reasoning is more a descriptive term to describe when machines can do complex decision-making tasks and they can reason with information. But it's machine learning is the field name. I think machine reasoning is really just a descriptive term. But yeah, again, I don't know that one for sure.
Yeah. Okay. I'm also not sure about machine reasoning. And a second question from Kemas Yuharja. In modeling Mauna Loa problem, how you come up with adding 2p? Can you explain it more detail? I think
the 2 pi here.
Yeah, 2 pi.
Oh, I mean, you don't actually have to use a pi here. So essentially, this x, I think, was measured in years. So you see, you've got, can you see my screen?
Yes.
Yeah, okay. So you've got this sort of periodic sort of fluctuation. And I think there's one period, there's one cycle every year. So when x increases by 1, you want to go through one entire cycle. And in the cosine function, this is periodic with a frequency of 2 pi. So every time x increases by 1, you multiply by the 2 pi, so it goes through one cycle. But yeah, it could be that the 2 pi, again, the 2 pi could be wrong. Maybe it's like 2 pi plus 0.01 or something. I don't know. And so this might be another example of the model not being 100% correct.
Okay, thank you. Next question from Finska Amalia Permadi, but she asked about information theory. And I think we will have this topic on the next lecture by Ian. So
yeah,
I think it's
Wednesday, I think.
Yes, on Wednesday. So yeah, I think she can learn from the next session on Wednesday. Okay, so the next question from Wahyu Hidayat. He mentioned about your example on forgetting your wallet while it is raining in Amsterdam. And okay, can you help him understand about joint probability and conditional probability? And can you please re-explain product rule and sum rule using that
Right.
analogy. Yes.
Okay, using this analogy. So
Yes.
I guess the joint probability it's the probability of two things happening together. So it's the probability, as you said, I forget my wallet and it is raining. This is, in a way, it's a single event, but it's made of two individual events. The conditional probability is the probability that I forgot my wallet because it was raining. So the raining has already happened. I cannot change that. That is a certain fact. But now I have forgotten my wallet. So one is when they happen together, and it could be that it's not raining and I have also forgotten my wallet. But in the conditional probability, it always rains. I cannot change that fact. That is a given. And in this product rule and the sum rule, this is just way. So the product rule is a way to relate the joint and the conditional probability. You can get some intuition as to why these rules are the way they are. It might just be easier to just learn them by heart and then gain the intuition later. But really the product rule is just, I say it's the definition of conditional probability, which is up here, just rewritten when you multiply both sides by this P of B term. And it's really, it's just a rewriting of the definition of conditional probability. The sum rule is, okay, so maybe this is a bit easier to understand. So the sum rule, so the probability that actually I could probably describe both of these in intuitive terms actually. So going back to the product rule, sorry. The probability that it's both raining and I have forgotten my wallet is the probability that it's raining in the first place. And then the probability that I forgot my wallet because it was raining. So you multiply these two together. The sum rule, so the probability that I forget my wallet is going to be the sum of forgetting my wallet and rainy, but also of forgetting my wallet and it's not raining. So this is why we do this sum. So because there are more than one way how I could forget my wallet. So yeah, we're summing over every possible event, raining or not raining.
Okay,
I hope that made sense.
Yeah, yeah. Okay, so next question from Muhammad Kamarul Arifin again. Does probability mass function essentially produce conditional probability of an event?
A probability mass function is not a conditional necessarily. It is just a marginal probability. So it would just be on this slide. Well, it's different actually. They're different things. So a probability mass function can be conditional, or it could be a joint, or it could be a marginal. These are just different incarnations of the thing. The probability mass function is really just a way to assign probability to discrete events. And then there's a related notion called a probability density function, which is about assigning probability to continuous events, but that's a bit more complicated to deal with. But it is independent from conditional stuff. You can make a conditional probability mass function. And you can make a non-conditional probability mass function. They are separate ideas.
Yeah, separate ideas. Okay, thank you. Next question from Rian Adam Rajagede. Okay, you mentioned that there are differences in the terms of probability, statistics, and machine learning based on how we see conditional probabilities on slide 40. Can you please explain more in that part?
Yeah, okay. So maybe this is a bit of, as I said, it's an overly simplistic slide. Again, you know, it's just to try and get a difference in understanding of these different things. So probability, for me at least, is just a way of to model how processes happen. It's just a way to model the fact that every time I observe the world, even if I'm doing the same, if I'm running the same experiment, I will get different data. Every time particles are emitted from my source, they decay at different distances. And statistics is the way of undoing that. So saying I've got my data, trying to find out what the underlying process is. What is the model given the data? In machine learning, and this shouldn't be machine learning, I should call it supervised learning or unsupervised learning in this particular case, or in this particular case, density modeling. This is saying I have data, I don't care which model. It's a very different way of thinking. I don't care what the actual true model is. I just want to create new data given the data that I've collected. I want to know if I were to observe my model one more time, where would I likely see my new decays? And I don't care which of the models I chose, because that's not actually what I'm interested in doing. So it might be I've collected lots of pictures of cats and dogs and orangutans, and then someone gives me a new picture and they say, you know, what is the probability that this is a dog? And then I can say, oh, this is like 0.9% like a dog, 0.05 cat, 0.05 orangutan. But this is a new data point, and this is what I'm interested in doing, prediction of new data points.
Okay, yeah. Next question is more about terminology, the terms. Okay, from Dwi Ari. We often hear the terms min, max, argmin, argmax, sub, and in. Those terms are usually very confusing when we are reading machine learning paper in the optimization section. Okay.
Yeah.
Could you explain to us what the difference among those terms?
Right. So max means, so basically, if you think of a, do I have a curve here? Okay, here we are. So if I've got this curve here, so this is my likelihood function before, and I've got lambda along the bottom. The max, basically max is basically the value of this function at its very highest point. So max would be this 0.0002 something over here. This is the value at the highest point. Min would be the value at the lowest point. And then argmax is the position where, so the position along the lambda axis, where either the max happens, or argmin is the position along this axis where the min happens. I hope that's clear.
Yeah, okay. So I think I will take one more question that's not very technically related to the to this topic, but I think it will help the participant to get other useful resources to understand this mathematics behind the machine learning. Okay, this is from Kemas Biharja. There are tons of mathematic things that we need to know in mastering machine learning. Okay, so this is just the beginning, the lecture one, but yes, most of your slide contains the mathematics symbol. Yeah, that's right. As prominent researchers in this field, could you advise us or the beginners how to understand the mathematics behind machine learning? Maybe can you advise some books or any other resources?
So there is a new book from last year, or maybe this year, called Mathematics for Machine Learning. This is, I think, a very, very good resource if you want to read about this. This is free online, so you can definitely find this. And these other 3 books at the start are also very good. I would say that this book by David Mackay is the best for giving you intuitions, and it teaches you the maths along the way. And also this other book, Pattern Recognition and Machine Learning, also teaches you a lot of the mathematics along the way. This one here, Kevin Murphy, is probably more at a higher level if you already know the mathematics. So I would say these 2 and this one here. As for the way how I learned a lot of this stuff, a lot of the time Wikipedia helps a lot. And also just Google. There's a lot of different universities doing a lot of courses, YouTube, a lot of lectures are online already. And the nice thing about YouTube is you can start and stop and you can rerun lectures. But I think it's really just a process of reading, seeing these things again, and you will get a good feel for them after a while. I think maybe the practical sessions later will help people a lot.
Yes, right. Okay, so we also will have several practical sessions to help the participants to understand the lecture better. Okay,
Yeah.
thank you very much, Daniel. So there are some questions that hasn't been answered since we already run out the time, and I will make a summary or a resume for the question, and maybe you will need 1 or 2 days later to answer some of the
Yeah,
questions.
sure.
And we
Just
we will share the answer from Daniel for the participant. Okay. Okay. Thank you very much for all who attending these sessions, and all of the session in MLSS Indo is a live stream in YouTube. So just in case you cannot attend a session, and then you can watch it later on YouTube. Okay. Thank you very much for Daniel. Okay. We will meet again in the next session with Said. Yeah. Okay. Let's have a break first. Okay. Thank you.
thanks.
We are channeling the company's artificial intelligence efforts into one recognizable organization, Qualcomm AI Research. Qualcomm invents breakthrough technology that transforms the way the world connects and communicates. Going beyond mobile chipsets, we're inventing AI technology that can be used across a wide range of products and industries, from mobile and automotive to smart homes and cities, ultimately changing the way people live for the better.
Machine learning has already entered every corner of the Qualcomm enterprise. I personally believe that Qualcomm is uniquely positioned to become a key player in on-device AI, which brings with it tremendous opportunities, such as increased data privacy for users, reliability of service, high speed and efficient use of bandwidth.
Today, machine learning algorithms such as deep learning use huge amounts of energy to power them. And as AI increasingly moves to low-power edge devices, energy efficiency becomes all the more important.
The challenge we face in the future is about squeezing as much as computation as possible out of every joule of energy. And Qualcomm has a long history of delivering technologies that do just that.
Our mission is to push the envelope of AI and machine learning in the areas that will significantly improve everyday life. We are asking challenging questions, like how do we preserve communication privacy? Can we use deep learning to compress videos? How can we eliminate uncertainty when making life and death decisions? And how can we use this knowledge to optimize Qualcomm chips that run machine learning algorithms?
Qualcomm AI Research is an inspiring environment where researchers collaborate, innovate, and share their findings with the world through high-impact publications. But we do so much more than just writing papers. We actually build AI solutions that are used in billions of devices, in your cell phone, your smartwatch, your drone, your car, and all the other innovative technology of the future.
So if you're interested in pushing the frontiers of artificial intelligence, machine learning or deep learning, and above all, if you feel passionate about the prospect of bringing ideas to life and impacting billions of people, then Qualcomm AI Research is the place for you.
Semua hal berangkat dari sebuah awal. Begitupun kami menjadi pionir. Memutar roda penggerak bangsa dan terus melaju. Kami hadir seperti sebuah keluarga. Dan terus fokus membangun perekonomian negeri. Menjadi yang terdepan, mewujudkan mimpi-mimpi besar. Dari atas awan kami terus bergerak dan berinovasi, melihat negeri ini tumbuh dan berkembang. Inilah kami yang tak akan pernah berhenti, mengantarkan Indonesia ke puncak kejayaan. dimanapun dan kapanpun, kami selalu hadir melayani dengan setulus hati.
History, most of the time, is born out of the simplest of acts, just like the birth of our story, starting with the pursuit to close the distance through voice and make exchanging of informations at your own fingertips. And who could have known that was just the first step of our long journey? We had to jump even higher, to open new dimensions of opportunities to explore the world. And we keep on transforming through different times so that we can bring joy and progress for all walks of life. The world is always spinning, just like the sun. Your loyalty in us has always been our light to keep on innovating. No more simple beginnings, further and ahead. We have to keep on running, for you, for Indonesia, with the same vigor that has been driving us from the day one we began our 55 years. Selalu ada untuk Indonesia.